Okay, let's talk about silicon carbon batteries. You've probably heard the name floating around, maybe even seen it in a few niche phones, but there's this idea that just won't go away, that they're somehow unproven or maybe even a little bit dangerous. So, why is there so much confusion? Let's actually dive into this and see if we can separate what's real from what's just fear.
And look, that idea got a huge boost when a major tech influencer like MKBHD said something like this. It really made a lot of people nervous. I mean, it makes you think, right? If the really big names are steering clear, there has to be a pretty good reason for it, doesn't there?
Well, that's the big question we're going to tackle. We're going to push past all those common fears you hear about performance and safety and really dig into what's actually holding this tech back from being in every single phone, tablet, and laptop we own. To really get what's going on, we have to start with a little bit of the science. See, at the very heart of this whole thing is a battle between two materials, both fighting to be the anode, which is the part of the battery that actually holds the charge. On one side, you've got the old champion, graphite, and on the other, the new challenger, silicone. So here is the night and day difference. In a normal battery, it takes six, you heard me, six carbon atoms in the graphite just to hang on to one single lithium ion. But with silicon, one single silicon atom can grab and hold four of them. The potential for cramming way more power into the exact same space is, well, it's just staggering. And that chemical advantage translates to a number that, honestly, feels like a typo. In theory, a pure silicone anode could hold 10 times more power than a graphite one. Yeah, 10x. Can you imagine a phone that lasts 10 times longer? It sounds like something straight out of science fiction. And for now, it kind of is science fiction. So here's the reality check. Right now, companies aren't using pure silicon. They're actually just mixing in a little bit, only about 15 to 20% silicon into the anode. So the result isn't that 10x jump, but it is a very real, very impressive 2 times boost in battery life. And you know what? Understanding that small percentage is the secret to busting some of the biggest myths about this technology. So let's get right into those myths, because you hear them all the time. There are three main fears that always pop up when people talk about silicon carbon batteries: that they expand, that they degrade quickly, and that they overheat. Let's tackle these one by one. This is the big one, right? People hear this wild number that silicon expands up to 300% when you charge it, and they immediately picture their phone turning into a balloon, or worse, just exploding. And yeah, that's a pretty terrifying thought. But that fear comes from a total misunderstanding of how these batteries are actually built. Remember, it's only a tiny part of the anode that's silicon, so the overall expansion is incredibly small. And engineers, well, they plan for this. They literally design the battery with little empty spaces for that tiny bit of silicon to safely expand into. A great way to think about it is like the gaps they leave in railway tracks so they don't buckle in the summer heat. It's not a flaw, it's just really clever engineering. Okay, the next big concern is longevity. The thinking usually goes something like this. Sure, you get more power today, but that battery's going to wear out way faster, and in a year or two, you'll wish you had a regular one. But when you actually look at the numbers, you find the complete opposite is true. Apple, for example, says their standard graphite batteries will hold about 80% of their capacity after 1,000 charges. But the brands using silicon carbon, they claim it takes 1,600 cycles to get to that same point. So they're not just matching the old tech on lifespan, they're promising to blow past it. And finally, we have the heat issue. If you're packing in more power and charging it way faster, doesn't that mean these batteries are going to run dangerously hot? Now, the answer to this is actually pretty fascinating. So yes, they can get warmer, but that's mostly just a side effect of being able to charge them so incredibly fast. But here's the wild twist. The very same chemical property that lets them charge that fast also makes them more stable. They are actually less likely to have a catastrophic explosive failure than old graphite batteries, and they even perform better in extreme hot and cold weather. So wait a minute. If the technology isn't exploding, it's not degrading faster, and it's not dangerously overheating, then what is the real problem? Why isn't it everywhere? Well, this is where it gets interesting, because the real hurdles are things we almost never talk about: business, shipping, and global politics. It really boils down to three big, kind of boring reasons why the major brands are dragging their feet. First, the surprisingly complicated world of international shipping regulations. Second, the manufacturing habits these companies have built up over decades. And third, the massive geopolitical reality of where battery parts actually come from.
Okay, so here's a rule I guarantee you've never heard of. There's an international regulation that says any single battery cell over 20 watt hours, that's about 5,400 milliamp hours for a phone, is considered dangerous goods. It can't just go on a regular plane, it has to be shipped in special containers on special cargo planes. And that, as you can imagine, adds a ton of cost and potential delays. So then you might be asking, how are some brands selling phones with these huge 8,000 milliamp hour batteries? Well, they use a really clever workaround, a dual cell design. Instead of one giant cell, they just use two smaller 4,000 milliamp hour cells. And since that limit is per cell, they're totally in the clear. But here's the catch. Huge companies like Apple and Samsung have built their entire design and R&D pipelines around single-cell batteries for years. And to change that now would be a massive, expensive headache. And then there's geopolitics. This is a huge one. Right now, China produces a staggering 92% of the world's battery anodes. Just think about that. If you are a company like Apple or Samsung and you need hundreds of millions of batteries, the idea of depending almost entirely on a single country for a brand new, absolutely critical component, well, that is a massive supply chain risk that makes them very, very nervous. So you put it all together, these tricky shipping rules, this resistance to changing manufacturing, these huge geopolitical risks, and it all leads us to the real reason why the big brands can afford to wait. It's an idea that we can call the presumption trap. Here's exactly how this trap works. We, as consumers, see a big trusted brand like Apple or Samsung taking their sweet time to adopt a new technology, and we automatically think, oh, they're just being extra careful. They're doing their due diligence to make sure it's safe for us. But when you factor in all those logistical and supply chain nightmares we just talked about, a much simpler reality appears. Their powerful brand loyalty means they just don't have to rush. They can afford to sit back and wait for someone else to solve all those expensive problems. And let's be real for a second. This idea that these brands wait because they're aiming for perfection is, well, it's a total myth. I mean, we all remember Bendgate with the iPhone 6, right? Or the Samsung Note 7 explosions. And that was with proven old-school graphite tech. Apple's butterfly keyboards were a legendary failure. The point here isn't to bash these companies. It's just to remember that being slower doesn't automatically mean you're being safer or better. So when you boil it all down, here's the big takeaway. The slow adoption of silicon-carbon batteries isn't a judgment on the technology itself. The tech works, it's safe, and it's already in products you can buy. The real delay is all about the boring, complicated, real-world problems of business, shipping rules, and global supply chains. And that leaves us with one last question to think about. Every time we automatically assume that slower is safer, we're kind of letting the market levers off the hook. So who really benefits when the biggest players in the game can afford to just sit back and wait for a new technology to get cheaper and easier to manage, all while we assume they're just looking out for our best interests? It's definitely something to think about the next time you hear about a risky new technology.